most of this week we're going to be actually exploring gravitational actions, which you've already met with David, but we'll kind of go back, review, maybe fill in some of the pieces. And in particular, we're also going to do a little bit of work on submanifolds so that we can make the gravitational action kind of consistent from a Lagrangian perspective. And I'm pretty sure David pointed out that it's a little bit dicey when you first go past. If you're doing the Einstein action just from the perspective of equations of motion in the bulk, the interior, then you kind of say, well, okay, it's not totally okay, but that, we still get the right Einstein equations in the bulk. But if you want to start doing things like actually calculating gravitational actions, which you might do if you want to start thinking a bit more about quantum gravity in the sense of quantum processes in gravity, not necessarily an underlying fundamental high-energy theory, then you need to be able to compute gravitational actions. And the problem with the Einstein action is it's kind of zero on all of these different Ricci flat solutions that are physically interesting and distinct. So that's where we're headed this week. But I didn't finish off what I wanted to say on Friday, so I thought I'd do that and at the same time kind of pull in some other bits and pieces about black holes that'll kind of motivate where we're going to go next. So I want to talk finish off sort of talking about, what happens in the neighborhood of an event horizon, and then kind of jump almost to the other side of being quite formal and talking a bit about black hole thermodynamics, because that's going to kind of motivate this action approach. So this is where we were on Friday. We'd derived a sort of geodesic equation in the form of a sort of a point particle motion in one dimension r in a potential well, which was V. And on the equator, V has this form. And what I was interested in doing was in trying to identify where the event horizon was of the Kerr black hole, because we found sort of two critical surfaces. One was where GRR blew up, and that was where this delta went to zero, and the other was the ergosphere. So that was where GTT was zero. So we wanted to kind of see which of these was the relevant surface from the perspective of the event horizon. So if we're looking for an event horizon, that's the boundary between things we see and things we don't see. And therefore, it's kind of a null surface because we're saying that light cannot escape. So what we're going to do is we're going to look at this geodesic equation on the equator, because the equator is where you've got the maximal difference between that GTT equals zero and GRR blowing up. And we'll look at null geodesics. And the one final simplification I want to make so a null geodesic is eta equals zero. We can rescale the affine parameter to set e equals 1. And just for algebraic I'm going to take GM equals A. So when GM equals A, delta now factorizes as a perfect square, and this is known as the extremal limit. If GM was any smaller than A, or if A was any bigger than GM, you wouldn't have a root of this quadratic. So that just makes things a little easier. So if I look at what my effective potential is, this term goes, that eta disappears, E is just 1, and so I have 1 plus V and I have basically the functional dependence of my potential is a 1 over r squared and a 1 over r cubed piece. So it's sort of quite simple. Now, I'm going to sort of think about geodesics escaping, and I'm going to sort of take a limit where I sort of have a light ray and bring it closer and closer to the black hole. So I'm on a scattering orbit, which means I have a minimum radius, and I'm just going to kind of turn and turn until that minimum radius gets arbitrarily close to the event horizon. So my initial conditions are going to be that r dot is 0 and r is some r min, which, you know, I'm going to argue that that's going to be bigger than or equal to a. So in other words, I'm going to be going for this as being my event horizon. So if I look at the condition for r dot is 0, if r dot is 0, then v is 0. And so 1 is equal to h squared minus a squared over r squared minus this second term. And my solution is h minus a. So you sort of see that because this is h minus a times h plus a. And so you have h plus a over h minus a here, and then minus 2a over h minus a, and that gives you 1. So the most conservative, given that the this second region where GTT goes to 0 is outside where delta goes to 0, the most conservative assumption I can make is that Rm is bigger than or equal to A. It could be a lot bigger, but at least it's bigger than or equal to A. And so this tells me that H is bigger than or equal to 2A. So that's my starting point. So what happens to that geodesic? Well, what happens is governed by the geodesic equation. So we look at that. So where the geodesic goes is going to depend on the gradient of V, just essentially by differentiating my nonlinear first-order differential equation for R. I differentiate that, and depending on V prime, the geodesic will either fall in or go out. So if I look at what V primed is at this value of R, it's 4a minus 2h over r min squared. And because h is bigger than or equal to 2a, this is less than or equal to 0. So because v primed is negative, R increases. So it's like saying, if I look locally, this is R min, this is V. It's saying that locally this is what our effective potential looks like. So we've come in from large R, we scatter and go back out. And that is true right up until Rm, the minimum value of R, is actually A, at which point everything kind of grinds to a halt. Once R, you're basically on the event horizon. So, what this tells us, or just confirms, that the event horizon is at delta is 0. So that is why I've been using the phrase ergo region and ergo horizon for GTT equals 0. Because it's still an important surface, but it's not the event horizon. You can still escape from within the ergo region, but you just can't be stationary within the ergo region, at least stationary with respect to an observer at infinity. So let's just look a little bit more at what happens around a black hole. So the first thing is that whilst it's a very good approximation to take the vacuum Schwarzschild or Kerr solution, because any matter around the black hole, it's so, relatively speaking, its impact on local curvature is tiny compared to the curvature coming from the black hole. Nonetheless, from our perspective, trying to observe black holes, this matter's important because it can still be sucked in, it can be sort of heated up, and therefore it can shine and it can send, photons back to us, which we can then see and infer things about what's happening in the neighborhood of the horizon. So in particular, what often happens, and I guess it depends on whether it's more like a sort of astrophysical black hole, just a few solar masses, or whether it's like a supermassive black hole. But either way, both of these black holes have quite, sort of messy environments. There's a lot of matter around the black hole, but from a perspective of, say, an astrophysical black hole, what will often happen is they occur in binary systems, and they've sort of sucked over time, they've sucked matter in, and the matter's formed this disk that's kind of spinning around the black hole, gradually, sort of as it radiates, gradually losing energy and falling closer and closer until it's sucked in. So I just want to say a little bit about talking about orbits around a black hole. And again, because I want to do it on the board and in as simple a way as possible, I'm going to talk about a sort of very idealized accretion disk around a Schwarzschild black hole. So a circular orbit obviously has R equals constant, and V equals V primed equals 0. So this effective potential, if R is a constant, R dot is 0, so V is 0, But in order for r not to change, you've also got to have v primed as 0. So I think when I first sketched v, I probably did something like this. So both of those little dots represent circular orbits. And you can kind of see that this one's going to be stable, because if you give it a little nudge, add a small amount of energy to that orbit, it'll just kind of wobble around in this well, whereas this one, if you give it a little nudge, it'll either go to the right or go to the left. So the picture, with cheerful disregard for what is actually corresponding to what you see, make the black hole bigger. This is not a picture of what you're going to see, this is a coordinate picture. So I'm going to give it I'm drawing a finite extent to sort of emphasize it's like a sort of disk thing. But let's suppose that the disk has some inner radius. So that's what we're kind of going to get towards accessing. So let's take Schwarzschild. And I'm only doing this really to make the algebra easier. It's quite fun to play with Kerr and GD6 and Kerr. So if I take A as 0, I'm interested in particle orbits. So we need eta equals 1, because we're looking at massive stuff in the neighborhood of the black hole. So I can read off what V is from the top, and I'm going to take, again, theta is pi on 2. So I'm just going to be very, very simplistic, take a completely flat disk on the equator of a black hole. So this is my effective potential for equatorial GD6 around a Schwarzschild black hole. I can find its derivative easily. And we're going to need the second derivative of V. So all I've done there is just done a little bit of differentiation. So our circular orbits are going to be V equals V primed to 0. And by looking at the sort of qualitative behavior of V, we kind of know that it's going to look something like that sketch that I drew up there, because we know that at large, well, I should have made it turn around, shouldn't I, at large R? Let me do that for the sake of accuracy. So at large R, V goes to a constant. You've then got the Newtonian 1 over R fall off, so it starts to dip. Then you hit the centrifugal barrier, it starts to rise. And then finally you hit the sort of GR plunge into the black hole. So we always know that V is qualitatively going to look like that, and whether or not you have a dip is going to depend on the relative magnitudes of H and M. So, you know, as you kind of move your circular orbit in, those two maximum and minima are going to move together. So, once we say our circular orbit is v equals v primed is 0, that then determines our angular momentum and our energy at a given radius. So we simply solve So we're sort of spotting 3GM there as being some sort of important surface from the perspective of geodesics. So depending on what you did, you'll know that there's an unstable circular null orbit around the Schwarzschild black hole at 3GM. But even though this is a massive particle, you're kind of sort of seeing some of these magic numbers kind of coming up. So let's evaluate V double primed at this place. So in terms of our circular orbits, if our circular orbit is outside 6GM, V double primed is positive, and so that tells us we have a stable circular orbit. However, at r equals 6GM, we have this sort of critical point where our V double primed is 0. And so we have a sort of our stable circular orbit is about to disappear. So it's called the innermost stable circular orbit, or ISCO for short. So if you're thinking about sort of observing an astrophysical black hole, this is kind of an important quantity. So inside, once you've got the particles that have got to this in an ideal Schwarzschild black hole, that have got to this innermost stable circular orbit, if they lose any more energy, they'll kind of fall in a bit more, and then they cannot orbit in a stable fashion, and so they will start to be sucked into the black hole. So that's kind of the innermost edge, in a sense, of this accretion disk. And also, again, if you think about what's going on as stuff is being gradually sort of sucked in and going around the black hole, the temperature of the emitted photons gradually goes up the closer and closer you get to the black hole, because, again, the curvature's going up, their velocity's going up, so it's more energetic. And so typically this has got a sort of very characteristic temperature which is associated to, I guess, to the radius that it's orbiting at. So this is sort of one way people try to measure or look at black holes in the sense of just looking at what are the photons coming from the black hole and what is the temperature, what is this sort of peak temperature for the accretion disk, because that peak temperature is telling you where the cisco is. So for Kerr, this radius drops.
Sorry, what is the peak temperature at the ISCO?
So you have a sort of typically the energy of photons coming out from the accretion disk gets bigger the further in they are. So if you're kind of looking, you'll see, I mean, at the moment, it's sort of how clean is it? If we had a perfect world, totally clean spectrum, we'd see a nice peak, which would correspond to the stuff that was being emitted from the inside of the disk. Okay. So the hotter that is, the closer into the black hole it is, right? And so it's important because for Kerr, our ISCO is less than 6 GM. And indeed for extremal Kerr, actually equals the horizon radius. So there's this notion that if you could sort of do a perfect observation, you'd be able to measure like how fast the black hole was rotating. So my hunch is you'll be hearing more about the other black holes, the supermassive black holes in strong gravity, which is, of course, the Event Horizon Telescope, which Perimeter's got quite a connection to. And that is more not so much from this type of clean or astrophysical type of accretion disk. That's more from just general stuff, as far as I understand anyway, falling into the black hole. And so, but again, the key is following the light that's being emitted by matter being sucked into the black hole, and therefore sort of sped up, heated up. And so what they're interested in is looking at this sort of imaging from the neighborhood of the black hole at the center of our galaxy. So this is a very simple-minded discussion of geodesics around black holes, but it's only simple-minded because I'm doing it on the blackboard and I'm doing everything, analytically insofar as possible. Obviously, if you want to figure out what you might see in a realistic environment, you've got to really roll your sleeves up, look at a realistic solution for the black hole, and look at realistic geodesics coming from near the event horizon, which is easiest to do numerically. And then on top of all that, this isn't just about the photons, you see, you've also got all the redshifting. So it's quite a complicated problem. Right, so having talked about looking at black holes, I'm going to do a complete 180 and think about black holes as theoretical objects. So, I want to start just thinking about black hole solutions. And at the moment, it's going to look a little bit naive. It's hot, isn't it? Do you want to prop the door open? We seem to be having trouble with this room. I want to now shift gears to looking at black hole thermodynamics and thinking about black hole thermodynamics. Now, I'm going to do this from a relatively naive point of view, in the sense of there are various ways that you can access the notion of black hole thermodynamics. There's various ways that you can derive the temperature of a black hole. But in practice, when we are faced with a solution with an event horizon and we want to know what is its temperature, what we tend to do is the easiest thing possible. Okay, so it's the principle of least action. So I'm going to kind of describe to you laws of thermodynamics via the principle of least effort. So for the Kerr black hole, I'm going to think about the event horizon. So our event horizon is at r plus. So r plus is the larger of the two roots of delta equals 0. So our area it's not quite 4 pi r plus squared, which you might have thought initially. You're sort of thinking, oh, well, if it's at r plus, then, you know, you're sort of, we're used to the r as meaning area of spheres. But that's not actually quite true in these Boyer-Lindquist coordinates. So if you sort of flick back to where I first introduced Kerr, you'll see I first of all wrote it down just as a dt squared, dt d phi squared, and then I kind of completed the squares in such a way that you had a sort of delta multiplying a dt minus a sine squared or a sine squared theta d phi piece. So on the horizon, that term is 0. And then if you looked at what remained, you had a sort of square of r squared plus a squared d phi. So this r squared plus a squared is coming from the bit multiplying d phi. So you need to integrate the root g d theta d phi over the event horizon. So that's where this is coming from. So that's telling you that r in Boyer-Lindquist is not obviously an areal coordinate. So we could also write this as, because our right. So because the event horizon is at delta is 0, if delta is 0, r squared plus a squared is 2gmr. So this is also 4 pi times 2gmr plus. So I'm just writing that because I might need it. But in particular, notice that if it were Schwarzschild, the area would be 4 pi r plus squared, and r plus would be 2gm. Here, r plus is less than 2gm, so this is less than the area of a Schwarzschild black hole. So again, we've got this notion, even though r is not anymore the areal radius, once a black hole starts to rotate, its horizon kind of shrinks relative to what you'd expect from its mass. Doesn't shrink, per se. Okay, so let's just have a look at what happens if I vary this area. So at the moment, I'm just playing around, basically. I'm just having a bit of a play, a bit of an explore in terms of exact solutions. So if the radius of my black hole changes because of some physical process, then if I want to know how it changes because possibly A is changing, and it certainly will change if R plus changes. So that's all I'm doing at the moment. But now I know what R plus is. I think I've written it somewhere. Oh, have I written it down? Yes, right in front of my nose. Okay, so now I know how to do delta R plus and get it in terms of delta M and delta A. Okay, so first I replace delta R plus. And I've simply, taken this expression and varied M and A. And this here is just the square root. R plus minus GM is the square root. And then if I tidy this up, I've now got things in terms of delta M and delta A. So again, I'm not, at the moment, I'm still playing. We're kind of going a little bit in the dark here, just seeing what happens and where we get to. Now, I'm going to recall what this parameter A is. So A is sort of representing the angular momentum, but it's equal to J over M. So my delta A is delta J over M minus J over M delta M over M. So of course J over M is just A. So that means I can replace my delta A in terms of delta angular momentum and delta mass. So So let me just substitute in what that gives me. So I've really just kind of written that slightly different. Oh, I've lost my delta M. So I've written it a little differently to kind of pull out this a common factor, if you like, here and here. But now let me look at what's multiplying delta J here. And I'm going to argue that this omega represents the angular velocity of the event horizon. So if we imagine what we mean by angular velocity, we know our black hole's rotating because we've got this dt d phi piece. So it's like saying there's a velocity in the phi direction. And the angular momentum of our solution is going to be the ratio of this g phi t to g phi phi. And as r goes to r plus, this is a over r plus squared plus a squared. So this we're going to interpret as the angular velocity of our black hole. Which means I can kind of rewrite this relation in terms of delta m. So I'm going to say, what is delta m equal to? Well, that's equal to r plus minus gm over r plus squared plus a squared So I've kind of grouped things together suggestively. And I want to compare this to the first law of thermodynamics. So in the first law of thermodynamics, you have a sort of change in your internal energy. I'm going to do it as internal energy for the moment, which is TdS, then a PdV term, which I'm just going to park for the time being, and then you have chemical potentials and charges. Now, the rotation, we sort of think of rotation, it's something that's conserved, so it's kind of a charge. So J does represent a charge for our black hole. So that last piece looks a bit like a chemical potential times a charge. The first piece on the right-hand side has something to do with area and then some other terms sitting in front. So this suggests that we have a sort of thermodynamic interpretation to our black holes with m corresponding to energy in some sense. We'll come back to that, so I'll put a little asterisk there. T with a temperature and an entropy. Now, this is just totally suggestive. Why did people take this seriously or start thinking, why did Bekenstein and Hawking start thinking about this as anything other than a sort of essentially meaningless analogy, just replacing one symbol with another? Well, it was actually thinking about thermodynamics just in general, in the universe. If you had a lot of entropy, so you have a system that's quite disordered, it seemed as if there was a thermodynamic paradox, because you could simply go along to your local black hole, throw all the junk inside the black hole, and it's gone, completely gone forever. Therefore, you've lost entropy. And so it seemed like black holes were completely inconsistent with thermodynamics, because you could just lower entropy by throwing things inside a black hole. However, in the 1960s, various theorems were being proved for black hole space-times. So you had the singularity theorems of Hawking and Penrose, saying that inside an event, or inside, strictly speaking, a trapped surface, but inside the event horizon there was a singularity. But another important theorem that had been proven was the fact that the area of a black hole always increases provided your energy, your local T naught naught, is positive. So this is an energy condition called the weak energy condition. If your local energy is positive, then the black hole horizon can never shrink. And so this notion of area being an increasing quantity is also really reminiscent of entropy being an increasing quantity in thermodynamics. And so Bekenstein sort of conjectured that maybe the area of the event horizon was also an entropy, contributing to the entropy of the universe. So that even if you threw something inside the black hole to try and get rid of it, the black hole would grow because it had fed, and therefore its entropy would go up. So that was kind of, at the time it's still, a little bit sort of, well, it kind of works if you do this. But there was no reason to assign a specific constant of proportionality for entropy to area. And so it wasn't until Stephen Hawking actually did a computation looking at field theory on a black hole background and comparing a sort of in vacuum to an out vacuum and seeing that they weren't the same. So the in vacuum did not transform to a vacuum at Scribe plus, but instead it looked like a thermal state at a particular temperature. And so that was, once you actually had a constant of proportionality, once you had an exact value of the temperature, then you got the constant of proportionality and hence the entropy. So this T goes to 1 over 8 pi gm for Schwarzschild. And that was what Stephen Hawking had calculated back in 1974. So once you know what the temperature is, you kind of know how to adjust all the constants, and you find that entropy is 1/4 of the area. So that is sort of beginning to flesh out and also to kind of bolster this interpretation of thermodynamics. So I'm not going to do Stephen's calculation, but I'm going to give you an alternative method of calculating temperature, which is the one that we actually use when we're faced with an event horizon. So let me explore this a bit more. So I'm going to take the Schwarzschild solution and I'm going to Wick rotate it. I'm going to send T to I tau. So what I get, if I just take the norm or the absolute value of ds squared, so all I do is I've got the same solution, but with everything plus. Now, this is a Ricci flat Euclidean solution, but what happens at 2gm? When we were in Lorentzian space, we could do an analytic extension across 2gm, and we found non-singular coordinates that were perfectly fine at the horizon and beyond. Here, if we go to r less than 2gm, our metric changes signature. It goes from plus 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 to minus minus plus plus, which that's kind of a bit of a dramatic change. So let's go in a bit more closely and look at what happens as r goes to 2gm. That should be a -1, sorry. So here we've kind of got dr over the square root of 2gm all squared as r goes to 2gm. So I can instead think of that as a proper distance. I can integrate that up. So let's try to find a proper distance from 2gm. So that means I need to take the square root, if you like, of 2gm. So I'm going to define a rho that is proportional to the square root of 2gm, and in the end I want my metric to start with d rho squared. So that tells me that 2 rho d rho is lambda dr, and also if I look at 1 minus 2gm on r, that's roughly rho squared on lambda times 2gm near the horizon. So if I now ask what does my metric look like, my Euclidean metric in the TR direction is essentially, so I've got to look at what happens to the dr squared piece. So dr squared is 4 rho squared on lambda squared d rho squared, so that's my dr squared. And that is divided by 1 minus 2gm on r, which is rho squared over 2gm lambda. So the rho squared terms cancel. One of the lambdas cancels. And then I've got 1 minus 2gm on r, which is rho squared over 2gm lambda, d tau squared. So here, if I take lambda is 8gm, then my ds squared is d rho squared plus rho squared d of tau over 4gm squared. So now I've got a proper distance away from 2gm, but the way I've rewritten the time coordinate sort of makes it look like rho squared d theta squared. So this looks like the origin of the real plane in polars, and it suggests that tau is periodic with periodicity 8 pi gm. Now, having a periodic Euclidean time is the way in which you do field theory at finite temperature. And the temperature is given by the inverse periodicity. In other words, T would be 1 over 8 pi gm here, which is exactly what you get when looking at the right-hand side. So this is actually completely fitting in with this notion that black holes are in a thermal state, and the temperature of that thermal state is 1 over 8 pi gm, at least for the Schwarzschild solution. So this was noticed by Gary Gibbons and Stephen Hawking later, sort of a couple of years after the sort of calculation of black hole temperature. And what they were trying to do, at the time at least, was think about Euclidean actions. And so they were, looking at evaluating the action for a black hole, realizing you had to add something to the Einstein action. And also they noticed that, hey, it's got a periodic Euclidean time, which is exactly what we would expect if the black hole was at a finite temperature. So that kind of is another way of sort of starting to coalesce, if you like, making more sense of this picture of black hole thermodynamics. So what about other charges? Well, we've got J and omega from Kerr. We also have, for Rice and Nordstrom, which David tells me you've seen, we also have charge, Q, and electrostatic potential, phi. But what I just want to finish off with here is coming back to this question that I parked, which was, what about P dV? So P we're thinking of as kind of a pressure. So what could a pressure be? So pressure could be the cosmological constant. So does that make sense? So in order to just examine whether this could possibly make any sense, I'm going to go back to the solution for a black hole with a cosmological constant. So I'm going to set you as an exercise so the Euclidean argument is saying rho squared is proportional to r minus r plus. So that I'm going to set that as an exercise to show that that gives t as the derivative of f at the horizon divided by 4 pi. So I'm going to do essentially what I did with Kerr. I'm going to perturb the horizon. So what that means is I take this relation, f of r plus is 0, and I essentially vary what that relation is. So I'm basically taking f plus delta f of r plus plus delta r plus is 0. So if I vary all the parameters in my solution, I get First of all, I've got to vary R plus, because if I throw something into the black hole, R plus changes. If I throw something into the black hole, M changes. And I'm going to just think about lambda changing as well. So here, if I want to know what the pressure could be, I'm going to define my P as lambda over 8 pi g. So that's pressure. The cosmological constant kind of tells me something about pressure. So if I rearrange this, I get delta M. So here my F plus is, of course, 4 pi t. My delta R plus is related to the change in area of the event horizon, because here R is indeed the areal radius. So I get T delta S. So if I substitute P for lambda up to 4 pi g, then what I'm left with is T delta S plus 4/3 pi r cubed delta P. And of course, that 4/3 pi r cubed is like a sort of geometric volume inside the event horizon. I'm not saying it's the actual volume, it's like a geometric volume. So this looks like TdS plus VdP. So it's not TdS minus PdV, but plus VdP. So this suggests that M is the enthalpy. So there's been a whole sort of literature and exploration of black holes with varying thermodynamic pressure. Your tutor, David Kubiznik, sort of been very active in this, so he's done a lot of work in exploring this particular relation. But you might sort of say, or one, you know, the sort of knee-jerk reaction when you see this is, but isn't lambda a constant, right? So how can lambda vary? Well, lambda can vary because if you have, let's say, a scalar field, its energy momentum is given in terms of its gradients and its potential. And if the potential is far greater than the gradient, so in other words, if the field moves slowly, then the scalar field energy momentum is potential dominated. So I'll just write that here. So you have an approximate cosmological constant, but if phi changes, then V changes, which gives lambda changing and P changing. So that's how you can get a varying lambda. And of course, this you probably saw is cosmological inflation. So time-varying lambda is not exactly unknown. It's just you have to shift what you mean by cosmological constant. So I'd better stop there. But this is sort of quite, you know, it's a very active area thinking about this aspect of black hole thermodynamic phenomenology or whatever. And if you want to find out more, ask the resident expert.
And about the last thing, please ask Ruth. Many papers on this now.
So, okay.